Good morning one and all. So, last two classes we have seen the membrane separation processes. In the first class we have probably discussed about the various modules available and basics of membrane separation process in food industry, where they are exactly used. In our second lecture, so we have seen specifically the four different membrane separation process, which are nothing but microfiltration, ultrafiltration, reverse osmosis and nanofiltration. And in the last class we told that where these five processes are being applied in food industry, in the general cases and applications, and what are all the modules available for each membrane separation process, everything we have seen. And also we have in depth discussed about microfiltration as well as ultrafiltration. In the ultrafiltration, we have ended our second lecture with the cheese making and fractionation of whey process. So, I will start from there with a small recap of fractionation of whey and other applications of ultrafiltration. In today's class, we are going to see about the nanofiltration and reverse osmosis and also electrodialysis. If time permits, we will do 2 or 3 problems. Actually, here I would like to mention about these membrane separation process. We are seeing it in application wise, right. So, we are not going to do in depth analysis of various membrane separation processes, because there are lot of modifications in it, and there are lot of theories, and also we are not discussing anything on the mathematical side of it, mathematical modeling or the calculations regarding the membrane separation process. So, we are mostly concentrating on the application side in food processing industry. So, what are all the membrane separation process are being used, and how do I choose the membrane for particular application. Okay. So, but still we will do certain problems on how to find out the osmotic pressure, and how to find out the retentate and permeate concentration, that we will do. Okay, so I will start with whatever we ended in the last class to make you remind a few things. So, fractionation of whey using ultrafiltration. So, that was done by the retentate is nothing but a non-casein protein, and along with some low molecular weight solute, so which are nothing but a lactose and mineral salts. So, ultrafiltration is used to fractionate this whey part, that is nothing but a valuable whey protein concentrate as a retentate, and the protein free permeate, which contains mainly lactose and minerals, these both comes in permeate, and the whey protein is concentrated. So, the retentate is usually concentrated further. Retentate is nothing but a valuable whey protein using a evaporation or spray dried, the further thermal processing. So, these two are thermal processing. Okay, so instead of going directly from the non-casein protein part of the whey to evaporate or spray dry, so if you use in between the membrane, so you can reduce the energy load which is being spent on evaporation or spray drying. So, these are all thermal processes. Okay, so then further these whey proteins are used for manufacturing of cheese and considerable array of food products and health food specialties. So, the process goes like this: the pre-treated pasteurized whey, so which is being fed into microfiltration membrane. So, from there we get the fat or curd residues. Then the permeate goes for another process, which is nothing but ultrafiltration. So, here is what the main process is being done. Then the permeate is collected and the retentate is further added with the diafiltration water. So, this diafiltration probably I have told you in the last class itself. The diafiltration also they use it as a separate membrane process. So, which is nothing but I will take the retentate of ultrafiltration and add some water and further go for another ultrafiltration module. So, this is nothing but a diafiltration. So, we add the diafiltration water in the retentate which comes from the first ultrafiltration module. Then further the permeates are getting collected as a lactose recovery, which is nothing but a purified concentration and spray drying. So, this lactose further fed into these processes, either spray drying or evaporation process. So, then the retentate is nothing but a whey protein concentrate, right. So, the permeate from the microfiltration comes into ultrafiltration. So, the retentate is taken and the diafiltration water is added into that and it goes for further ultrafiltration. The retentate after second ultrafiltration is nothing but a whey protein concentrate. The permeate is further purified and concentrated and goes for spray drying to remove the lactose. So, the other applications of ultrafiltration is used for clarification of clear or microfiltered fruit juices, and if appropriate membranes are used. So, the ultrafiltration also we have given the ranges, right. So, the range of pore size and range of the pressure applied also, right. So, if the appropriate membranes are chosen between the range where my microorganisms get filtered, then this ultrafiltered juices are practically free of microorganisms, right. So, the range, the pore size range what I have to choose is, so that should be able to retain the microorganism. If that is the case, so we call it as a cold pasteurization or cold sterilization without applying the thermal processing. So, the use of ultrafiltration for the concentration and fractionation of plant protein extracts also suggested. So, the ultrafiltration membranes we use to concentrate and fractionation of plant protein. So, one such case is soybean protein production. So, the ultrafiltration membrane is used. So, in this defatted soy flour is extracted with the water at high pH. So, the aqueous extract is then concentrated by ultrafiltration. So, the process is here. So, first defatted soy flour and the one alkali and water, this is fed into the tank. So, this is further pumped to the decanter. So, decanter does the separation based on the density. So, the high density part of the feed is getting collected in the bottom. The clear upper part will further pumped into the microfiltration module. So, the concentrated part we call it as a okara. So, this is nothing but a soy pulp, right. So, the further the clear the upper portion will be further fed into the microfiltration, then the permeate is further sent to the ultrafiltration. So, from the ultrafiltration we collect the permeate as a waste, then the retentate is further added with the diafiltration water and further concentrated using the ultrafiltration. So, the permeate goes as a waste, the retentate is nothing but a soy protein extract, so which goes further for precipitation. The other applications of ultrafiltration is the sugar, I actually here itself. So, this is we have used twice, right, the ultrafiltration module. First we remove the permeate and take the retentate and add the diafiltration water, then further we go for a ultrafiltration, we collect the permeate and retentate. So, this also further you can do more 2 or 3 times, right. So, the sugars and other low molecular weight solutes may be partially removed by repeated steps of dilution and ultrafiltration. So, that is nothing but a diafiltration, dilution and further ultrafiltration, which is nothing but a diafiltration. So, this we continue these steps and produce the purified and concentrated soy protein extract for further processing. So, this also can be done. So, the soy protein extract at what percentage you wanted. So, based on that number of ultrafiltration modules can be added further. Okay. So, the UF is used commercially as an alternative to evaporative concentration in the production of gelatin as well. So, for this gelatin production also this ultrafiltration membrane is used as an alternative to evaporation. So, today we mostly concentrate on reverse osmosis and nanofiltration. So, most these both techniques have much of overlap. So, I will tell what is the exact difference in couple of slides after. So, the reverse osmosis, the major application is water desalination. So, this we are all know. The moment we say the reverse osmosis, so the first thing comes into our mind is water desalination. And wastewater treatment and water softening. Water softening is nothing but ions removal, the unwanted ions removal from the water. The RO and NF in the food industry is, however, for concentrating the liquid foods by membrane removal of water. So, reverse osmosis, water desalination, most of the applications are related to wastewater treatment, but here in food industry, so where we use reverse osmosis is nothing but to concentrate the liquid foods by membrane removal of water. By removing water, how do we concentrate? So, this can be done by evaporation as well. So, to do by evaporation, I need to add the heat, right. So, but here with the membrane itself, by applying the reverse osmotic pressure, I can remove the water from the liquid food, right, to concentrate them further. The advantage is tremendous saving in the energy expenditure, as I told. So, the heat is not being applied here, and elimination of the risk of thermal damage of the product. Obviously, if you are not using the heat for processing, then you can avoid the thermal damage. And better retention of volatile aromas, since we are not applying the heat, the volatile aromas gets retained. So, then your food also looks fresh. Then lower capital investment. So, we are not investing anything large on this part, because it is just a membrane process. We do not need to employ any heat transfer equipments, that is why the lower capital cost. And the limitation wise, fluids of low osmotic pressure and relatively low viscosity. So, in the reverse osmosis, because you are applying the pressure against the osmotic pressure, so if these processes can be applied only for fluids with low osmotic pressure. That means salts, most of the time salts cannot be handled, because they have a high osmotic pressure compared to other materials, and a relatively low viscosity product only can be handled. And the process of pre-concentration before final concentration by evaporation. This is not a limitation. So, this is the advantage, right. So, before going for evaporation, so for example, I need to have some 70% of this concentrated solids. So, I can do up to 40% using any RO, and after that remaining 30% can be done by evaporation. Okay. So, in that case, so you are reducing the energy load which is given if we go for directly evaporation. And pre-concentration of maple sap was one of the first specific applications of RO in food processing industry. So, this is nothing but a plant protein. Okay. So, when the reverse osmosis was tried in the food industry, the first one, the pre-concentration was done in the maple sap. So, this is maple sap or maple water, because it is a extremely diluted solution containing an average of 2.5% soluble solid. So, that means 2.5 degrees of Brix. This is a unit, right. So, the sugar content of an aqueous solution, right. 1 gram of sucrose in 100 grams of solution, and represents the strength of the solution as a percentage by mass, right. So, 2.5% soluble solids, that I can express in terms of 2.5 degrees Brix. So, this is nothing but a 1 gram sugar in 100 grams of solution. So, that is nothing but 1 Brix unit. Okay. So, if the solution contains dissolved solids other than pure sucrose, then Bx only approximates the dissolved solid contents. Okay. So, the unit is Bx, which is nothing but a Brix. Okay. So, this is just to tell you about the unit, but what we are discussing is the maple sap, which is an extremely diluted solution, containing an average of 2.5 percentage soluble solid. So, where how the reverse osmosis is being used to concentrate this maple sap, that is what the process is. The sap must be concentrated to 66 to 68 Bx. So, that means 66 percentage of the soluble solids is being concentrated using a reverse osmosis by removing about 96 kg of water from every 100 kg of sap. Remember, almost 96 kgs of water which contains in the 100 kg of sap, right. So, this is a huge quantity of water, 96 kg from every 100 kg of sap. So, typically, so 75 percentage to 80 percentage of this quantity of water can be removed by RO. So, that means 96 kg I am having. So, in that almost 75 to 80 percentage of water, kg of water can be removed by using reverse osmosis. Then further amount of water can be removed using evaporation or drying. Okay. So, without increasing the osmotic pressure and viscosity to unacceptable levels. So, one may think, okay, 96 kg of water can be removed, why can't it we do in reverse osmosis at one go, right. So, but what restricts me to do so is the osmotic pressure and viscosity, right. So, when you remove the water, the soluble solids gets concentrated. So, the viscosity should not go unacceptable level. So, that in that case I may not be able to apply the reverse osmosis. The same way, when you concentrate further and further, the osmotic pressure also gets increased, right. So, you need to push them again the membrane surface. So, in that case, so these two are limiting parameters which limits me. So, how much percentage of the water from 96 kg of water can be removed. So, that these two based on osmotic pressure and viscosity of the solution, then 75 to 80 percentage of the 96 kg of water is removed. The intermediate product in the sense, first we have told here. So, it is almost 96 kg of water per 100 kg of sap. So, in this I will remove I removed 75 to 80 percentage of the water using RO. So, the remaining product we call it as a intermediate product, intermediate concentrated product. So, intermediate concentrated product. Okay. So, this is intermediate product to the standard concentration of commercial maple syrup. So, only 20 to 25 percentage of the water has to be removed by subsequent evaporation. So, the maple syrup is highly concentrated one. Okay. So, what we are doing here, maple syrup which is nothing but a 2.5 percentage of the solid content. So, that is being processed using membrane separation which is nothing but a RO and evaporation to get the maple syrup. So, in that RO part is almost 75 to 80 percentage of 96 kg of water per 100 kg of sap. The maple sap has relatively high tolerance to high temperature. So, in that case RO is carried out at 80 degrees centigrade and above, resulting in higher capacity and improved microbiological safety. So, this food is tolerant to temperature. So, the RO process is carried out at higher temperature which is nothing but a 80 degrees centigrade. So, which gives us the microbiologically safe food with higher capacity. And one must also be careful, because the membrane separation process we are doing it only twofold. One is to reduce the energy consumption, and if my food has the large particulate solids, then how to handle. So, for that purpose also we move to membrane separation. The other advantage is, since we are not using the high temperature process, my volatile aromas get retained, right, and also nutritional quantity. So, here we are mainly concentrating on the microbial safety, that is why we are going for 80 degrees centigrade, and one must ensure at this temperature the nutrient quality as well as the volatile aroma, if the food is of having these two advantage, or if the food is having lot of volatile aroma or nutritional content. So, we need to think about why we are processing at this high temperature of 80 degrees centigrade. That is what probably we are doing it in thermal processing as well. So, the RO concentration of very dilute solutions concerns aromas and aqueous extracts of herbs and teas. So, in this case, so the RO is applied for to retain the aromas as well as when we process the extracts of herbs and teas. So, we need to be processing at lower temperature. Okay, so that is why my choice is RO to get the aqueous extracts of herbs and teas. And concentration of fruit and vegetable juices, mostly apple, citrus fruits and pineapple, there also RO has been investigated, the process of RO has been investigated extensively. And pre-concentration of tomato juice is particularly interesting because of its relatively low initial concentration. So, which is about 4 to 5 Brix. So, here we are mainly concentrating the tomato juice using RO. So, instead of going for evaporation. And RO pre-concentration of fruit juices is usually carried to an upper concentration limit of 20 to 30 Brix, right. So, here the pre-concentration is done using RO, the final concentration is done using evaporation or drying technique. The same way orange juice to 36 Brix by RO at a TMPD of, TMPD is nothing but transmembrane pressure difference. Okay. So, the orange juice to 36 Brix by RO at a TMPD of 6 megapascal, but the concentrate was devoid of the characteristic of aroma and fresh juice. This is what I just mentioned, right. So, we can go for higher temperature and higher concentrations, and also we need, which restricts me is to go for higher concentration. One is osmotic pressure and the viscosity of the product, but if we process at higher temperature, I feel like that is microbiologically safe. But the thing is, we also look into what happens to the characteristic aroma of the food product, right. So, the more and more temperature you go, that the aroma will get decreased. So, that is the reason I choose RO, right. So, when you choose RO to concentrate any liquid product to pre-concentration, so these are all the important and critical factors we need to also keep in mind. So, if I go for higher temperature process, what happens to volatile aroma, and if we are going for a higher concentration, so how much osmotic pressure I need to apply and what is the viscosity of the product. So, this restricts me. So, what temperature I need to process my reverse osmosis, or what concentration I need to choose for pre-concentration of liquid food. The tomato juice tolerates well high temperatures, and usually RO treated at temperatures above 60 degree for tomato juice. The juices containing suspended particles are first clarified by microfiltration, and only the clear filtrate or serum is concentrated by RO. If desired, the removed pulp is added back to the RO concentrate for cloudiness and aroma, right. So, even for ultrafiltration, this is what we have seen, right. The first, the juices or any product, any food product, what we do is we first clarified using a microfiltration, then we are sending to ultrafiltration. Here also same way. So, the suspended particles are first clarified using microfiltration, then fed into RO process. So, if desired, removed pulp is added back. Removed pulp in the sense, the whatever you removed from the microfiltration can be added after the reverse osmosis process to get the aroma and fresh taste. Okay. So, the RO is applied to whole milk, skim milk and whey. So, milk processing also RO is being applied. RO concentrated whole milk is used in the manufacture of cheese, yogurt and ice cream. So, for these manufacture cheese, yogurt, ice cream manufacturing, the concentration of whole milk can be done using reverse osmosis process as well. The pre-concentration of milk and other dairy fluids prior to conventional evaporative concentration and drying. So, the pre-concentration of milk and other dairy fluids. So, prior to conventional evaporative concentration and drying, the RO is being used, and concentration of liquid egg by RO is also reported. The lower molecular weight and its hydrophilic nature, the ethanol is only partially rejected by RO membranes, right. So, the ethanol concentration also can be done using a reverse osmosis membrane, but here due to low molecular weight, also its hydrophilic nature restricts the RO membrane in ethanol concentration, because what happens is the ethanol is partially rejected and your permeate also will have the ethanol component, right. So, some of the ethanol is transported to the permeate, while practically all other solutes including flavor aroma compounds are retained. So, when you process the alcohol with the RO membrane, right. So, the retentate here is flavors and aroma. The permeate is nothing but will have alcohol as well. Permeate will also contain partial amount. Okay. So, the alcohol and water, the main is the permeate component is water. So, the water plus alcohol in the permeate may be separated and recovered by distillation to remove the alcohol component. So, the diluting the retentate with the recovered water, a beverage with full aroma but reduced alcohol content is obtained. So, whatever we got as a retentate here, so that will be added with the water, right. So, the retentate includes the solutes, flavors and aroma. The permeate includes alcohol and water. So, this alcohol and water component further distilled, distillation is nothing but another thermal processing only. So, we apply the heat, right. So, here you have a low boiling as well as high boiling mixture. So, the low boiling one will get evaporated first and gets collected as a condensate. The higher boiling one will come later, right, or taken as a bottom product. Okay. So, that is the way I separate the alcohol and water. This water, separated water from the permeate, again added into the retentate which has the solutes, flavors and aroma. So, this is the partial amount of alcohol is already removed, right. So, that means the one what I prepare now is a beverage with full aroma but reduced alcohol content, right. So, the what I have is the flavor component, aroma plus some solutes, and also the alcohol is also there, partial alcohol, because the partial alcohol only goes into permeate, right. So, in the permeate I will have water and alcohol, further it is distilled to remove the water. So, that water is fed back. So, that means some of the alcohol went into permeate. So, that I am not adding. The beverage now contains only the aroma and solutes without much alcohol content. So, that means reduced alcohol content. So, now the admixture of the recovered alcohol to the original beverage results in a product with increased alcohol content. So, what I did? So, here in the distillation I removed the water and alcohol. The water I have went back and added in the retentate. So, the removed alcohol can be added into the original beverage and the product will be having higher or increased alcohol content, the original product, right. Original product will have certain alcohol content. If this alcohol is also added, so that particular beverage contains the higher amount of alcohol content. Another application of RO is in the wine industry, is the concentration of grape must. So, the grape must is the fresh juice which is not brewed. So, the fresh juice which has the fruit pulps also. So, the concentration of grape must also the RO is used. So, RO and NF are being increasingly used for the pre-concentration of thin juices in the production of sugar from the beaten cane, right. So, when we produce the sugar from sugar cane, so there also the RO and NF process are being used to pre-concentrate the thin juices. And condensate of evaporators. So, evaporator we have seen, right. So, we take the dilute solution and we apply heat, right. So, the water gets evaporated, right. So, when you further condense that water, so that is called evaporator condensate, right. So, the condensate of evaporators are not pure water, but containing varying amount of organic matter. So, when the water evaporates, it also carries some of the organic matter, we cannot say that is a pure water. So, the treatment of these condensates by RO or NF helps recover important quantities of high quality water and reduces the cost of water disposal. So, what did we say? The whatever the condensate, whatever the vapor comes out of the evaporator, we condense it. So, that is called evaporator condensate. So, this also has some of the organic matter, because whatever the material I am processing in the evaporator which may have organic matter. So, when the water evaporates, it also carries with some of the organic matter with it. So, because of that, the condensate whatever I am getting from the evaporator, so that is not of pure water, right. So, this condensates after cooled, it is sent to the RO or nanofiltration membrane. So, which removes those organic matter and produces the high quality water, right. And one thing is I am getting high quality water, another point of view, in the cost effective matter I am also reducing the cost of waste disposal. So, that means, so if you have to throw this condensate with all organic matter, you have a certain environmental regulations, right. So, that is not that easy process. So, you are also getting the high quality water and also you are reducing the cost of waste disposal. So, this particular process is called condensate polishing, right, the condensate polishing. So, there my RO and nanofiltration membranes are being used. So, now nanofiltration. So, certain applications I also told commonly for RO as well as nanofiltration. So, now we are going to see what is exactly the difference between the reverse osmosis as well as nanofiltration. So, the RO deals with the removal of organic solvent from edible oil micella. So, the micella is nothing but a solution resulting from the extraction of oil by organic solvent. So, that is nothing but a micella. It is used in the extraction of oil, right. So, extraction of oil is done using the organic solvents. So, whatever the solution you get, that is nothing but a micella. So, the RO deals with the removal of organic solvents. So, the micella contains the organic solvents as well as whatever the component to be removed from the oil. So, to remove the organic solvents from the edible oil micella, the RO is being used. So, in the same process, nanofiltration membranes also can be used, because the membranes used here are nanofiltration membranes resistant to oil and organic solvents. The apt one to be used instead of RO is nothing but a nanofiltration membrane. So, that means the particular application of removal of oil from organic solvents. So, we can use RO as well as nanofiltration. So, if you see before, here also we are using RO or nanofiltration to polish the condensate, right. So, that means what is the difference between them, why they can be used interchangeably, right. So, the key difference between RO and NF is nothing but a rejection of monovalent ions and cations, right. So, the key difference between reverse osmosis and nanofiltration is nothing but a rejection of monovalent anions and cations, while the rejection of monovalent ions by RO membrane is practically absolute. So, absolute means the RO membranes remove completely monovalent ions, but your nanofiltration membranes rejected them to the particular extent only. So, it cannot reject the monovalent ions fully, right. So, this depends, the partial removal of the monovalent ions based on the extent of penetration depending on the type of membrane, concentration of the feed and TMPD, right. So, why it is partially removing the monovalent ions is because of these three major factors. So, the partial amount, right, whether it is a 10 percentage or 20 percentage or 30 percentage. So, the percentage of removal or extent of monovalent ions removal is based on the type of membrane we use and the concentration of the feed and the transmembrane pressure difference. So, because of that nanofiltration is sometimes called as leaky RO. Leaky RO in the sense RO could retain monovalent ions, but nanofiltration could retain them partially. Because of that it is called leaky reverse osmosis process. The polyvalent ions are preferentially rejected by nanofiltration. For non-charged molecules, the cutoff molecular weight is on the order of 100 to 300 Daltons. The being less dense than RO membranes, the nanofiltration membranes are less dense compared to RO membranes. The permeate flux can be achieved by nanofiltration at lower TMPD, right. The same permeate flux can be achieved by nanofiltration at lower MPD, because what we are doing now is we are comparing just reverse osmosis and nanofiltration. So, nanofiltration membranes are less dense compared to RO membranes. So, to get the same permeate flux by nanofiltration, I can apply only lower TMPD compared to the reverse osmosis process. Furthermore, since monovalent ions pass through the membrane, the osmotic pressure difference, which is nothing but a del phi, is lower in nanofiltration membrane compared to reverse osmosis. So, this is particularly important in fluids containing mineral salts, because we have already told for mineral salts osmotic pressure is high. So, when we process the mineral salts through nanofiltration membrane, so the process can be done at lower osmotic pressure difference. The nanofiltration is advantageously used for demineralization and deacidification of UF permeate of whey, right. So, whatever the permeate we get it from the ultrafiltration membrane, so that can be further deacidified using nanofiltration, right. The permeate of whey which comes out of the ultrafiltration can be further deacidified using nanofiltration membrane. Another important application of nanofiltration is water softening, where the preferential retention of bivalent ions of calcium and magnesium produces hardness free permeate. So, Ca2 plus Mg2 plus, these bivalent ions are removed from the water using nanofiltration, that is called water softening. So, if you remember in the earlier slide itself I told, right, the water softening is nothing but the hardness of the water is removed. So, the hardness mainly comes from the bivalent ions, which is nothing but calcium 2 plus and magnesium 2 plus ions. So, that is being removed using nanofiltration. So, the last one is electrodialysis. Till now we have seen ultrafiltration, first microfiltration, ultrafiltration, then reverse osmosis and then nanofiltration. So, nanofiltration and reverse osmosis can be used interchangeably, but nanofiltration has certain advantages over reverse osmosis. But remember, the monovalent ions are partially removed using nanofiltration, but that is completely removed using reverse osmosis. So, based on your application you have to choose, though nanofiltration shows some of the advantages over reverse osmosis, we supposed to choose based on the process what we are going to apply, what membrane process to be chosen. The electrodialysis is an electrochemical membrane process by which ions are transported through the perm selective membranes under the effect of an electric field, right. So, electric field is a driving force here. It is an electrochemical membrane process by which ions are transported through perm selective membranes under electric field. Electrodialysis membranes are sheets of ion exchange material. So, the ion exchange material is nothing but it exchanges particular ions only. The ions are separated by ED membranes according to their charge, right, whether it is an anion or cation. So, ED is most commonly used for the transfer of ions into or from the pumpable fluids, right. So, whether to remove the ions or add the ions in the sense in food processing sometimes we told, right. So, if there is any nutrient quality is deficient, so we can also add them during the process to get the particular nutrient level. So, there one of the application may be the addition of ions, ionic components. So, ED is most commonly used for the transfer of ions into or from the pumpable fluids. One of the first uses of ED was the desalination of brackish water. So, the water desalination only, the first electrodialysis was applied. The application wise, desalting and demineralization, deacidification or acidification of liquid food. So, deacidification you supposed to remove the ions, acidification you supposed to add ions. So, that is what here we meant. And electromigration of green tea catechins and phenol separation. Phenol is also nothing but a partially charged. Okay. So, we can use ED process for phenolic component separation as well. The assembly consists of alternating anionic and cationic membrane. So, these are nothing but a ion exchange membrane which permeate only particular ion, arranged in a stake similar to the plate frame configuration. Plate frame membrane module we have already seen. The anionic or anion exchanger membranes are permeable to anions and reject cations. The cationic or cation exchanger membranes are permeable to cations and reject anions. Okay. So, here is the diagram. So, the example here it is taken as a sea water. So, this AEM is nothing but a anionic exchanging anionic exchange membrane. So, CEM is cation exchange membrane. Okay. So, the your anion and cation exchange membrane is stacked in a alternative manner. So, your sea water is being fed into in between two anionic and cationic exchanging membrane. So, here you have a anode which is nothing but a positive electrode, here we have a cathode which is nothing but a negative electrode. The feed, right. So, here we have seen as an example as we have taken sea water as an example, but this can be your fluid particles as well. So, if you see your electrode is not being in touch with the product whatever you are using for the separation. Okay. So, here the electrolyte solution is being used. Electrolyte solution is used in both the places, electrolyte solution. Okay. So, now first we will see, so here electrolyte solution, so this is Na plus and so this is NO3 minus, blue one is NO3 minus, the red one is Na plus ions, right. So, the anion is nothing but a negatively charged, the cation is nothing but positive, right. So, the anion tends to accumulate near the anode because it is a positive electrode, the cations tend to accumulate near the cathode which is a positive ion. So, the anion pass through anion exchange membrane, the cations pass through cation exchange membrane. So, when you are feeding the sea water here, so the NO3 plus and Cl minus tend to pass through the anionic exchanging membrane. So, which allows the negative charge, right. The same way Na plus and K plus, the positively charged ions pass through the CEM, right. So, then it gets concentrated in this particular space. Why? Because when the cations moves here, so it has a cation exchanging membrane. So, when the anion moves this side, it will not allow further. So, the Na plus and Cl minus gets accumulated here. Then if you see the next compartment, the NO3 passes through the anion exchange membrane, and K plus and Na plus will pass through the cation exchange membrane. Then here in this particular space, they get concentrated. So, this is the way we collect the concentrate from this and you have a dilutant which is free of ions, right, because the ions moved through the ion exchange membrane. So, you collect the diluate. Okay. So, this is the electrodialysis process. So, you have two ion exchange membranes which passes specifically either anion or cation. So, the anion pass through the anionic exchange membrane and gets collected near the anode, and cation pass through the cationic exchange membrane and gets collected near the cathode. And also remember, your product is not being in touch with the electrode because that will be taken care by the electrode solution. So, from this, wherever the concentrate is concentrated, we collect the concentrate which is nothing but a salt particle, organic salts, and wherever the salts is removed, so that is nothing but a dilute. So, if you want pure water, so the diluate is nothing but your pure water. So, the more discriminating selectivity among ions of the same charge depends on pore size of the membrane. So, what we have seen here is, so I have taken two molecule, right, Na plus and K plus, right, in terms of cation. So, if I want to remove only Na plus, so that can be done by the pore size, right. Based on the pore size, I can remove even from same cations. So, I can further differentiate them into K plus Na plus by taking care of the pore size of the membrane, whether only K plus to be removed or Na plus to be removed. The pore size of commercial ED membranes varies between 10 and 100 Armstrong. And one of the first applications of ED in food processing was the partial deacidification of fruit juices that are too sour to be acceptable. Right. If the acid content is more, we feel that sour taste. So, to remove the acid component or deacidification of fruit juices, the ED was first employed in the food processing industry. Although the acidity can be reduced by precipitation of the acid, so commonly citric or malic acid, as a calcium salt, or by adsorption on an anionic exchanger in OH form. The D is nothing but the electrodialysis deacidification has the greater advantage of avoiding addition of chemicals. So, the thing is, the deacidification in earlier also, before applying ED, the deacidification in industries were done by either one of these mechanisms. One is the precipitation of acid using the calcium salt, and or adsorption of an anionic exchanger in the OH form, right. So, both the ways the deacidification can be done, but still the ED deacidification has the greater advantage because we are not adding any chemicals here, right. So, that is the way the ED is advantageous one compared to commercial precipitation of acid using the calcium salt. So, here the acidity can be reduced in two ways. One is adsorption of anion in OH form. So, other way is adding calcium salt, okay, and precipitate. Okay. So, this is conventionally followed, but when you apply ED here, right, that is advantage compared to normal precipitation using calcium salt. And the high mineral content of whey and whey products is sometimes undesirable, particularly when material is intended for infant feeding. So, that means the high mineral content in the whey or whey products. So, there also electrodialysis provides technologically sound method for demineralizing whey and desalting products such as soy sauce, right. So, these two applications also electrodialysis is being used. So, in the fundamental calculation wise, we supposed to calculate the water flux, right. So, for that the formula being used is J equal to Ka del P minus del phi. So, the J is nothing but a permeate flux, so which is kg per hour. Okay. So, where K is nothing but the mass transfer coefficient, so which is in the unit of kg per meter squared per hour and Pascal. Okay. So, del P and del A in Pascal. So, your del P is nothing but a applied pressure, so which is also in Pascal. So, del pi is nothing but your osmotic pressure, which is also in Pascal. So, A is nothing but a area, which is in meter square. Okay. So, this is pi, which is nothing but a osmotic pressure. So, your M is nothing but a in terms of concentration. So, this is your phi is nothing but a osmotic pressure, so which is in Pascal. Okay. So, your R is nothing but, so which is in Pascal, your R is nothing but a gas constant, which is nothing but kilojoules per kilomole Kelvin, right. So, kilojoules per kilomole Kelvin. So, your T is in Kelvin, T is nothing but a temperature. So, this is nothing but kilomole per meter cube. So, this is nothing but the M, right. So, that is nothing but a concentration, M is nothing but a concentration. So, the kilomole gets cancelled, Kelvin get cancelled, you will get kilo, joule is nothing but Newton meter. So, this is nothing but meter cube, so which is nothing but meter square. So, it is nothing but kilo Newton per meter square. So, we call it as a kPa. Okay. So, your whatever the osmotic pressure you calculate, which will be in kPa, right. So, kilopascal. So, your M is nothing but a concentration here. So, that is nothing but moles per meter cube, kilomoles per meter cube, and your R is nothing but a gas constant, kilojoules per kilomole Kelvin. The T is nothing but Kelvin get cancelled, kilomole get cancelled. So, kilojoules per meter cube. So, kilo Newton meter, joule is nothing but a Newton meter. So, kilo Newton per meter squared, which is in kPa. So, this is the way you can calculate osmotic pressure. Pi is nothing but M or T, M is concentration, R is gas constant, T is temperature. So, after calculating the osmotic pressure difference, you can go back and substitute in the flux equation. So, this is osmotic pressure, this is applied pressure, K is nothing but a mass transfer coefficient, A is area. So, you will get your permeate flux in terms of kg per hour here. Okay. So, if you apply your mass transfer coefficient in terms of kg meter squared hour Pascal. So, if possible we will do 1 or 2 problems in next class, and these are all the resources and additional references what I have used in this lecture. Thank you.